Assalamualaikum. My name is Nik Shami and I'm going to present the introduction. Okay, the problem and solution is the aircraft require high velocity to generate lift. In situation with limited runway length, aerocatapult systems are used to rapidly accelerate the aircraft. This provides the kinetic energy needed to increase airflow over the wings, allowing for takeoff within a very short distance. A method widely applied in aircraft carrier and UAV operation. The project scope is this project focuses on the design and analysis of small-scale aerocatapult for a lightweight airplane. We apply fluid mechanics principles, specifically airflow velocity, lift versus drag, and pressure distribution to demonstrate how aerodynamic theory governs a practical launch system.
Assalamualaikum, and my name is Idzham. My metric number is 28602, and I will present the slide of theoretical background. Okay, the catapult glider flight is controlled by fluid mechanism as they move through air. There are two main force that air connect, which is lift and drag. Lift is the one that keep it on the air, and drag is the one that slow it down. Lift can be calculated by using the half rho v square multiplied by c and r, where rho is the density of the air, and v is the airflow velocity, s is the wing area, and cl is the lift coefficient. This shows that small change in design or launch condition can affect the flight distance. The key of aerodynamic factor include the lift coefficient, drag coefficient, airflow velocity, and wing area, all of which influence how far and smoothly the glider will fly.
For the methodology, in the design phase, we research various glider variants and analyze its shapes that can result in longer and further flight. We then implemented the elements from various aircraft and gliders into the design and construction of our glider. For the assembly, we chose foam as our main material due to its lightweight and flexible nature of the material. However, the material is easily deformed when put under pressure or sudden impact, such as during landing. To counteract this, we put a wooden stick inside the fuselage and wings to reinforce the foam so that it does not break easily. Hot glue gun and elephant glue were used to attach and combine all the pieces of the glider together, as this glue is strong and lightweight, making sure the glider is intact during launch and flight. On top of that, several test flights were conducted before the testing day to find further improvements for the glider. For instance, when we tested our glider, we found that the joints in the wings were fragile and easily broken. To combat this, we used electrical tape in the fragile area to make sure the joints in the fragile part are stronger and able to withstand strong forces.
Okay, now we're going to the result and observation. We have 3 trial and each trial for the first trial is 473 centimeter, second trial is 488 centimeter, and third trial is 396 centimeter. And the hang time for trial 1 is 1.01 second and for second is 1.41 second, which is longer and further. So the observation is our glider remain intact with only main damage and minor damage observed at the nose area during landing, and catapult structure and string show no damage after all trial.
So moving on our CFD analysis, here we are comparing the airflow velocity between our two airfoil choices. There is NACA 2421 and NACA 4412. As you can see from the simulation, the air accelerates significantly over the curved upper surface of both wings, and it will be represented by the red zones. But there is a clear difference performance. For the NACA 4412, on the bottom side shows a much higher velocity acceleration. This is due to its greater chamber, which suggests it has a significant better potential for generating lift. On the other hand, the NACA 2421 on the top side is a much thicker profile, and the thickness is 21%. So the result of the thickness is slower airflow recovery and potentially higher form drag, which is not ideal for the rapid acceleration that we need for our AEROCATAPULT launch. Next, we look at the pressure distribution, which is the direct mechanism behind the lift. According to the Bernoulli principle, lift is generated by the pressure difference between top and bottom surface. In this situation, the blue areas represent low pressure, while the green and red area represented a higher pressure. As you can see, the NACA 4412 clearly larger and more intense low pressure zone on the upper surface. This proved the superior lift generation capabilities, while the NACA 2421 shows a less aggressive pressure gradient because it creates less of the critical pressure difference and it's less efficient for the short distance takeoff comparing to the NACA 4412. We can confirm the NACA 4412 is the best for the aerodynamic AEROCATAPULT.
Okay, now we move to conclusion. For the conclusion, first we design a two-dimensional glider F4 and create a flow domain around it. The domain was meshed with the final element near the F4 surface. Element then apply velocity inlet and pressure outlet boundaries, condition and assume steady incompressible flow. CFD will conduct to obtain velocity streamline, pressure content and lift also drag value for this analysis.
Based on our design challenge and flight testing, we have 3 recommendations for our future improvement. Firstly, we need to have a hybrid wing design. We can optimizing the performance by using the thicker NACA 2421 at the wing root for structural strength and then transition it to the high lift NACA 4412 for the main span. This gives us the best function of both. There is strength where we connect to the fuselage and the efficiency where we generate lift. Secondly, we need to upgrade the structural reinforcement during our testing. Face so many issues with fragile joint that required a temporary repair with with tape and glue. So we recommend replacing this with the internal carbon fiber rods or continuous spars. So that will increase the integrity and will reduce weight without adding external drag. Last but not least, we need to improve our impact resistance because we notice form deformation at the nose after several landing. So reinforcing the nose with high density foam or a protective coating can prevent the damage and make sure the glider remain reusable for a consistent data collection across multiple flight.